Hello, chemist and biochemist. In this video, what I'd like to talk to you about is uncompetitive inhibition. Now, I like to compare uncompetitive inhibition directly to competitive inhibition. Those are the two that I personally think are the first ones that you want to begin kind of analyzing and becoming comfortable with. Once you feel comfortable with competitive and uncompetitive inhibition, then I recommend moving on to a discussion of non-competitive or mixed inhibition, but not until you feel comfortable with these first two types of inhibition. Now, with uncompetitive inhibition, we're going to look at it in a couple of different ways, or I'd like to talk about it in a couple of different ways. The first way that I'd like to talk about uncompetitive inhibition is with the E plus S. So the enzyme plus substrate. Where does an uncompetitive inhibitor work into this sort of scenario? Well, the uncompetitive inhibitor is going to work in the following way. So if we have our enzyme plus our substrate, which is going to produce our enzyme substrate complex, and in the absence of an inhibitor, that enzyme substrate complex is going to go on to form a product represented by P and return the enzyme to its free, unadulterated state, or its unsubstrate or product bound state. Okay, so if we understand this, then the way that you can look at an uncompetitive inhibitor is what it's binding to. The uncompetitive inhibitor is going to bind to this ES complex. And what that's going to do is that's going to form what's known as an ESI or EIS complex. It's a complex that consists of the enzyme, the substrate, and the inhibitor. So what that means is that the inhibitor doesn't bind to the free enzyme, and although highly unlikely that it ever would, it also doesn't bind to the free substrate, but instead that complex together. So one of the ways that I always kind of like to visualize it or think about it is, let's imagine that we have our free enzyme right here, our substrate represented by this molecule right here. Well, enzyme plus substrate is going to form something like this right here. So this is our E, this is our S. And I always like to imagine it as some cleft or some surface between the enzyme substrate or the enzyme and the substrate, the interface between those, or something about the enzyme has changed to facilitate the inhibitor binding. Okay, so there's kind of a graphical representation, or there's kind of an illustrative representation. Now, the next way that I like to think about this is, how is this going to impact our kinetic parameters, our Km and our Vmax? Well, both your Km and your Vmax are going to decrease in the presence of a uncompetitive inhibitor. Now, this is something that Vmax going down, okay, that kind of makes sense. That's a little bit straightforward to me, just because, well, an inhibitor, it should slow down a reaction, or you would expect it to slow down or stop a reaction. So your Vmax is going to decrease. Now, what's a little bit tricky is Km. Because when I personally think about Km, I think about the Km as being a measurement of affinity. And if your Km goes down, that means the enzyme's affinity for the natural substrate increases. And personally, I think about an enzyme having a lower affinity, therefore, a lower Km, therefore a higher affinity for a substrate. I would think of as kind of a good thing, because that means that it's binding to it more tightly. So this is a little bit odd. The inhibitor is causing the affinity that the enzyme has for the substrate to go up. Well, why is that? Now, one of the ways that I personally think about it is, I always like to think about round numbers. So let's say that you have 100 copies, I'm going back up here, you have 100 copies of the enzyme. And let's just say that you have an infinite amount of the substrate. Well, all 100, just for this scenario, all 100 of those copies of the enzyme are going to form this ES complex. The enzyme and the substrate are going to pair together to make that ES complex. Now, let's say that when that ES complex is formed, then let's say 20 of the ES complex are going to go down here to form this ESI complex. So out of 100 copies of your enzyme, 20 of them are diverted to this enzyme substrate inhibitor complex, which means that at the end of kind of one round of that reaction, you're left with 80 copies of the enzyme. So what that means is for that subsequent round, when your inhibitor or when your enzyme is going back to bind to the substrate to continue propagating, continue producing your product, well, now you've lost 20%. And if you continue doing this, so in round two, rather than 100 copies of the enzyme, you only have 80 copies of the enzyme plus an infinite amount of the substrate. Let's say again, a number of those enzymes are sequestered as this ESI complex. What's slowly but surely going to happen is the free enzyme is going to be diverted, or basically the free enzyme's concentration is going to be decreasing for every single kind of round that this enzyme is going on. And so what that's going to mean is the free enzyme, or the pool of free enzyme that's available, is going to be decreasing. So what that's going to mean is basically those free enzymes are going to be fighting for that inhibitor. So their affinity for that inhibitor is going to go up, which means that their substrate constant, or sorry, their Km is going to be going down. Okay, so the net takeaway though is your kinetic parameters with an uncompetitive inhibitor, your Km and your Vmax will decrease. And I didn't even write this at the top of the page here, but an uncompetitive inhibitor is going to cause these things to happen. Okay. Now, the last ways that I like to think about this is I like to think about it first with a Michaelis-Menten plot, and then with a Lineweaver-Burke plot. Now, Michaelis-Menten plot, what I'm going to do is draw one graph or one line represented by no inhibitor present. Okay, so just a rough idea with my red line here, no inhibitor. Okay, now I'm going to switch colors to show what this is going to look like with an uncompetitive inhibitor. Now, the thing is that Km and the Vmax are going to go down. So what this is going to mean is that our line here is going to go up a lot steeper, a lot earlier, but then it's going to plateau also quite significantly earlier. Because if you remember your Vmax, and with a Michaelis-Menten plot, we have a y-axis, that's our initial velocity, our x-axis is our substrate concentration. So our Km is going down, which if we wanted to plot our Km for this green line, it would be approximately, well, what's our Vmax? Right here. Vmax divided by 2 is approximately right there. And here is the new Km. Compared to our original Km, which I'm going to be plotting in blue, well, I have to know my Vmax is approximately there. Half of my Vmax for the no inhibitor present is going to be about there. So looking at this red line, and it just happens that these two lines intersect. This is our Km with no inhibitor. Okay, so there's a Michaelis-Menten plot. We have a more steep incline, but then a sooner plateau because our Vmax has decreased. Now, the next graph that I wanted to show y'all is the graph or graphing of this same data, but as a double reciprocal plot, a Lineweaver-Burke plot. The Lineweaver-Burke plot, if you remember, we look at this with our y-axis being 1 over initial velocity and our x-axis being 1 over substrate concentration. Well, in red, here's my no inhibitor. And I'm going to plot it in, let's go with this kind of baby blue, sky blue. That's going to be plus inhibitor. So what's happened is my x-axis corresponds to my -1 over Km. My y-axis is 1 over Vmax. These two values have gone farther from 0. They are reciprocal values, though, So they have both decreased. Your Km and your Vmax has decreased. Now, what's a pretty common thing of a uncompetitive inhibitor is that your plus inhibitor and no inhibitor lines are almost completely parallel to one another because your Vmax and your Km have basically changed at essentially the same rate. Okay, so your takeaway whenever you're talking about an uncompetitive inhibitor. One, it's only going to bind the enzyme substrate complex. Two, the Km, the affinity, the Km is going to go down. So your affinity for your substrate goes up. Km goes down. Vmax also goes down. That's in the presence of an uncompetitive inhibitor. All right. Well, I think it's great to compare a competitive inhibitor and an uncompetitive inhibitor, understand those two with respect to one another. I hope this was helpful, and I hope you have a good one.